Okay, hello everyone. So I'm going to talk about a trace-based tennis coaching platform and smart training platform using artificial intelligence and computer vision. So for today's agenda, I'm going to first talk about an introduction to the topics and related works. Second, I'm going to go over our solution and approaches to the issue. Then we're going to talk about the experimentation for this research project. And finally, we're going to talk about some conclusions and potential improvements for the project. So first, let me present this. So first, let me introduce the topic. So first, for a lot of new tennis players, it's often a lot harder to self-monitor their own progress. So there's often a trade-off between having a coach and practicing independently. So having a coach means that you have to give up financial inputs in order to have good feedback. However, with practicing a lot of swings and a lot of serves, you can do that independently. However, without a coach, you give up this ability to self-monitor. So you don't have a guarantee that all of the things you're practicing are guaranteed to be good. So what this results in is a lot of tennis players turning to YouTube of videos of professionals like Federer doing swings. However, comparing this is often difficult. So to demonstrate, we can look at two videos, one of a beginner and one of a professional. So as you can see, the beginner swing is probably a lot different from how a professional would swing. This is Federer also swinging as a practice. During actual plays, he actually swings much faster than this. But I hope we kind of demonstrated that there's a lot of key differences between the swing of a beginner and the swing of a professional. So not only is a beginner swing a little bit more clunky and less fluid, but also different parts of the swing have different swing speed compared to professionals. So maybe beginners would start off a bit slower than professionals and then kind of force their way through, but professionals have an overall pretty fluid motion the entire way. So using computer science, using AI and computer vision, we hope to accomplish this. So first, let's introduce some related works. So these are three related works that I mainly found very prevalent to what I'm doing. So the first one talks about is classification of tennis shots with a neural network approach. Unlike our visual approach, this approach uses a lot of accelerometers, gyroscopes, and magnetometers to use the data from those to classify different tennis shots. They mainly classify tennis shots in 5 categories using forehand, topspin, forehand slice, backhand topspin, backhand slice, and serves. So using the data from all of those different categories, they're able to classify different tennis shots. Our approach is very different to theirs because our approach obtains data purely visually instead of using biological signals. The second one is using spatial temporal graph neural network approach. This one essentially uses visual data from different perspectives to get a 3D data structure of a person's pose and to analyze their motion that way. So using graph theory, they're able to use nodes of key landmarks of a person using 3D data and classify their tennis actions that way. So they're using a motion capture system. And finally, the last one dives into the deep learning methods for specific actions in tennis. So this one is mainly to recognize the strengths of different types of neural networks in classifying tennis actions. So our solutions. So in this section, I'm just going to talk about the different our different approaches to this question. So we want to synchronize. We want to make it easier for tennis players to approach comparing their own videos with the videos of professionals. So essentially, we want to adjust different parts of the video to synchronize the video of a person that's relatively new with a person that might be more seasoned. So that different parts of their serve, although they're at different levels, will sync up and kind of play simultaneously. So this is an overview of how everything would work. Our program is built through Python. The main algorithms are built using Python, using an algorithm or a library called MediaPipe. However, we want to make an accessible way for users to be able to input their data and to be able to access this algorithm through another means. So we built a website using Flask. So on the website, people would input their videos and to upload 2 videos, one of their own serve and one of a professional. The data from those from the website end would be sent to the controller, which would then feed the data into processing algorithms, which either uses unsupervised classification or supervised classification determined by the user's choice. After the algorithms are finished running, data would be sent back to the controller, which would go back to the website, and the templates would control what the websites look like. So the library we're using is MediaPipe. So to analyze the position and action of tennis players, we have to use MediaPipe's post-estimation package to create a skeleton of the person. So this GIF kind of shows what that action looks like. So as a person is doing some sort of motion, MediaPipe's framework plots these landmarks and gives you positions of different parts of the body. So for example, left shoulder, right shoulder, left elbow, right elbow, those types of different landmarks are all predicted using MediaPipe's pose estimation. So since the pose of a tennis player is generally the same, but other parts of the video, such as the background, can vary significantly, we'll only use a skeleton generated from MediaPipe instead of considering the entire image. So a lot of times you'll see tennis players being in a very crowded situation with the background being like bluish, but in other situations, the background can vary significantly, but the background in our situation really doesn't matter. So we will only look at the skeleton. So to simplify this further, we'll look at several angles within the skeleton. So for example, the angle between your arm and also your body, and also the angle between your legs, and also the angle formed on your elbows. So all of these different types of angles. And this can really just be calculated through mathematical means using the 2D or 3D data points that is predicted using MediaPipe. So for this is an introduction to how our process actually works. So let me alternate between this and this. So this is the actual parts of the processing algorithm. So first, after we upload an image, this will be fed to the processing algorithm. So using MediaPipe, the unsupervised model would label different parts of the video with different different labels. So this is just an example. So let's say if a video has 17 frames. So it might give us a label that's kind of like this array here. So 3 1s 0 0 0, 2 3 2 2, etc. Essentially, all the different labels are just showing different frames that are within this video that are similar to each other. So for example, the first 3 frames and maybe the last few frames might be kind of similar. So in that case, it'll label it with the same label. So what the unsupervised model does is it basically looks at the it basically compares different frames, and it looks at which ones are most similar, and it outputs a label array like this. So for the unsupervised model, we will run this for both videos, and it'll produce an array for both of these. The key issue here is that the labels doesn't have to match up between the videos. So a label of 0 in video 1 doesn't necessarily have to be similar with a label of 0 in video 2. And another challenge of this is that oftentimes we'll see labels where it goes from 1 2 3 2 1, where it alternates back and forth. So in those cases, we'll consider this kind of noisy. So we also have to run several processing algorithms to do this. And I also mentioned that we also have a supervised learning approach to this. The difference between supervised and unsupervised in this case was that this trained supervised model would already know which labels is which. So a label of 0 would signify the start of a tennis serve. Label of 1 would become when the player kind of raises their arms. And so those are all dependent on pre-trained models. So with the supervised model, we already know which labels correspond to which. So after this array is generated, several processing algorithms are run. So first, as you can see through this figure, after you generated this array, another array is generated where it talks, where it kind of essentially says which parts of the frames are starting and ending. So if I switch from a label of 1 to a label of 0, and that will show like a key part of the video has changed. So you change from a group of very similar frames to another group of frames that might be kind of different from this. And in this process, it ignores group clusters of frames that are length of 2 or less. So if if frame 3 and 4 are labeled as something different, and then it switches back, that's not going to be a very big difference in terms of a long video, since there's going to be a lot of frames. So it essentially ignores those, and it creates an array of these kind of intervals. After these intervals are created, we're going to take midpoints of all of these intervals. So we're going to take a middle of the frame interval and basically compare it to the second video. Comparing it to the second video allows us to see which frames from the first video are similar to the second video. So in this case, for example, matching the matching the label 1 from video 1 might be matching with label 0 of video 2. So in that case, it'll match up all of these different videos and to kind of understand the relationship between different frames across videos that way. This processing algorithm is essentially the same for both supervised and unsupervised learning, although there is slight differences in how we applied it, but essentially in practice, it's identical. Before I go into experimentation, I can just demonstrate on, I guess, in real time how this entire thing works. So this is the backend. I'm just starting up the server here. So this is just a local server, and I can just go on my computer to demonstrate what this would look like. I apologize if it takes a little while. Okay, I'm just gonna skip over the description here because it goes into a little bit of the descriptions. But here, after you go on the website, you are able to select videos. I'm just gonna choose 2 videos that I already have on here. So you're able to upload this. So after the data from this website end is uploaded, it sends it into this the Flask. So it sends it into this Python end here. So everything will be processed on here. So yeah, so first it'll print out this array. This array is essentially what I talked about the labeling array. So this is using unsupervised learning, and it basically gave us this array for the first video that tells us which frames are very similar. And it does the same for the second video. And through processing algorithms, it'll kind of simplify it down, and also to adjust different parts of the video with different speeds. So you don't really see that, but the first 2 videos are the original 2. As you can see, the first video started kind of early. The second video, let me just play this again. The second video started much later, and it also had different speeds throughout. So a lot of adjustments are needed in order to actually sync these 2 up. So if you look at the bottom 2 images, they're playing pretty much at the same speed. Different parts of their serves are adjusted, and different critical times of their serves are matched up with each other. So all of those times, such as when they hit the ball, are matched up. When they start the serve is also matched up. So it allows players to make a lot more accurate comparisons between their serve and potentially a pro's serve. And also through the because we're ignoring background, we're only taking a look at the skeleton of the people. The background here, we intentionally chose to be very contrasting colors. So we have a blue background with kind of like a white indoor environment. Yet for the second one, we're choosing a red background kind of with an outdoor environment. But it doesn't really matter in our case because we only look at the skeleton image. So as you can see, we kind of eliminated a lot of potential affecting factors by doing that. So let me stop running this. Okay, so to continue, we did some experimentation to ensure that a lot of this one is mainly for the supervised learning portion, to ensure that the supervised learning portion is accurately getting the data and predicting the frames of the video correctly. So we compared several learning methods in supervised learning, specifically 5 different learning methods, or 6 if you're including changing several weights. So the first one is nearest centroid. We chose nearest component, nearest neighbor analysis, and also support vector machine. The nearest neighbor method has 2 kind of subparts of it. One is using uniform weights, and one is using weights that is represented by the distance of the players predicted. So as you can see here, the results of all of those situations, to mimic real life kind of differences in like camera angle, we also added augmentations to so such as like zoom in, like tilting the image, like kind of flipping the image horizontally and vertically, and those kind of different situations. So as you can see, different ones compared differently with and without data augmentation. More specifically, we tested the accuracy of different algorithms with different augmentations applied, and we tested it in 2 ways. So
ஆமா ஆக்சிஜன்
I
இல்லையோ
think someone
தொட்டிக்கிறதோ
is unmuted. Okay. So I think someone else is unmuted. But so for this one, we tested different augmentations in several or in 2 different ways. So first we have 4 different types of augmentations: zoom, tilt, skew, and rotation. So with all of these data currently shown on the screen, we're applying these individually. So for R, it represents how specific methods tested with only rotation applied. With S, it means how specific algorithms test with only skew applied. With different combinations of these RS, it doesn't mean that both are applied. It means that within this data set, we have both videos or both images that are either zoomed or either rotated. So these are not combined. But as you can see, different ones perform differently. But for this one, we're specifically doing combinations of augmentations. So RS would mean zoom plus rotation, RT would mean rotation plus tilt, etc. And so all of these perform differently in different situations as well. So using this, we kind of came up with nearest component analysis performed the best because it also not only did it perform pretty accurately across all areas, but it also was relatively faster compared to many other methods. I kind of already went over the conclusions, but we concluded that both supervised and unsupervised learning provided a good avenue of methods for tennis players to be able to compare their own progress with professionals. And as we saw through the demonstration, the results were pretty accurate, although there weren't many improvements that we can make. So one of such improvements is to improve the processing time for videos. Currently, if the videos are much longer, the runtime increases drastically. So we can definitely improve on the runtime, and also we can improve on the accuracy of both predictions as well. Yeah, can do questions. Does anyone have any questions?